Good morning and welcome. My name's Richard Kane. I lead the Analytics and Innovation branch in the Biosecurity Strategy and Reform Division of the Department of Agriculture. Before we sort of kick off everything, I'd like to acknowledge the traditional owners of the many lands on which we meet. And I acknowledge the traditional custodians of the land we are meeting on today. For me in Canberra, this is the Ngunnawal people. I acknowledge and respect their continuing culture and contribution they make to the life of this city and this region. I extend that recognition to the traditional custodians of all other lands on which our staff and participants are gathered here today, and to all Aboriginal and Torres Strait Islander peoples attending today's fantastic event. No pressure, Andrew. Before we kick off, just asking everyone just to keep your microphones on mute and your cameras off, if that's okay. Towards the end of this CEBRAnar, as we're calling it, there'll be an opportunity for questions. I think we've also got Michael Ormsby, who's already joined us, but you can either do that by putting your hand up, or you can type it into the chat, and we'll fire away with everyone. It's also being recorded, so just in case anyone has any issues, it should flash up there on the screen to let you know. For those not familiar, or you should be, but the Centre of Excellence for Biosecurity Risk Analysis, or CEBRA, is a long-standing biosecurity research initiative, plays a vital role in providing the Australian and New Zealand governments with expert biosecurity risk analysis and advice that helps inform both governments' responses to managing biosecurity risks. Today's webinar will feature work undertaken by CEBRA in collaboration with New Zealand MPI, and I think Michael's online as well already early, so thank you, Michael, to develop a model that estimates the value of various activities, including surveillance, readiness and border interventions by pest, and in this particular case, the gypsy moth. To explain more on this topic, you should have there at the top of your screen the presenter, Professor Andrew Robertson, who's also the CEO and Chief Investigator with CEBRA. Welcome, Andrew. Professor Robertson has a PhD in forestry and a master's in statistics from the University of Minnesota, and is currently Professor in Applied Statistics at the Uni of Melbourne. He's also an elected member of the International Statistical Institute and has published 4 books, over 90 research articles, and 50 CEBRA, or CEBRA as we call it now, technical reports on various aspects of risk analysis and biosecurity. New Zealand MPI's research lead for this work is Michael Ormsby, who's the Manager of Plant Risk Analysis in the Animal and Plant Healthcare Directorate of Biosecurity New Zealand. He's joining us all the way across the ditch from Wellington, so welcome, Michael, and he'll be available at the end of this presentation for any questions that we may want to ask. Thank you, Michael. Can see you all. Perfect. Look, without further ado, I'm going to hand over to Professor Robertson. You should be able to see that on your screen, and with about 10 minutes to go, we'll look to open it up to question and answers for the panel. Over to you, Professor Robertson. Thank you.
Thanks so much, Rich. I am poised. I'm wearing my special shirt with my lucky buttons. I've got a cup of tea, and I'm ready to get down to business. Today's CEBRAnar is it's going to be covering work that has been stewing for a number of years with Michael at New Zealand MPI. It's been, to overuse an already overused phrase, it's been a journey of a project. We've arrived at somewhere really interesting. I think this is fabulous stuff, but we'll be interested to hear what people have to say about it. So here we go. The traditional overview, I'm going to talk a little bit about the context and why we did it. And then I'm going to talk about pre-border and border interventions and how we model them. And then I'll talk about post-border stuff, and then the mechanics of the model, and then the results. Now, as Rich said, I am Professor of Statistics, and I know that gives me some serious chop when it comes to technical things, but I guarantee that there are no equations in this entire presentation, which I might add is a consequence of extraordinary self-control on my part. So the goal for the project, the high-level goal, is to determine the proportional impact of interventions against gypsy moth. Actually, it was a number of pests, and we developed the method whilst working on other pests. But gypsy moth is where the process sort of reached its full effulgence, its greatest peak. And the subsidiary interest is to assess specific counterfactuals. Specifically, there is specific surveillance for gypsy moth in certain areas in New Zealand. Well, what if that surveillance weren't there? And there are aspects of the system that are prepared for the potential arrival of gypsy moth. And what if in a counterfactual scenario, we weren't ready for gypsy moth? And I know that that's kind of a weird one to think about, but what's the benefit of readiness or preparedness against the arrival of gypsy moth, perhaps as an indicator of the value of investing in readiness or preparedness against other pests? And the key overarching value that's going to inform everything that we do is to keep it simple, please. A dictum warmly pressed upon us by certain Ministry for Primary Industry executives, and we interpreted that to mean, I think we're right, that utility should trump biology. So for everyone who's of a sort of biological mean in the presentation, I apologize deeply for the violence that I'm about to do to your discipline. So we start off then with the big picture. Now, this is probably the last thing you want to see at this point of the presentation, all these garish colors. And I don't know if you can see my pointer. Can anyone let me know if you can see my pointer?
Yes, we can.
Thank you so much. I'm going to split the model into two distinct and important parts, the establishment part and the costs part. The establishment part is a very simple pipelines pathway style model where amounts of material pour into a particular pipe, and things happen to them along the way, and then they pour out at the end of the pipe. And the things that happen, well, we have volumes that are contaminated at certain rates, and then measures occur, for example, cold treatment or sterile insect technologies, and so pre-border inspection and so on, and they arrive at the border, and then things happen to them at the border. I'm being very vague and hand-wavy, I know, but I'll be more specific for our pest. Things happen at the border, and this attenuates the arrival of the pest, and it translates to a propagule pressure, which is then attenuated. I'll talk more about that in a moment, to become an establishment rate. So the pre-border and border model is all about what is the rate at which the pest establishes. And it's key that we translate this whole model into that one number, because that one number is something that we can observe. And all the stuff before it, some of it we can observe, some of it we can't observe, but actually all of it we can think about. We can translate into quantities that we could observe if we were extremely, if we spent a lot of money and spent a lot of time. We could observe all of those, the things that happen, but we know what the establishment rate is. So it gives us a sort of point of truth. And we also do know something about the border inspections because we have inspection data, but that's less, I think, of a point of truth, arguably, than the establishment rate. So the pre-border model and the pre-border/border model, that one more is all about getting to the establishment rate. Now, the post-border model is, okay, what happens if it establishes? So if it establishes, the key unknown, there's lots of things that we know about how much a pest costs or what the impact is when it establishes. We may know where the host material is, we may know where the climate is suitable, we may know where it has been delivered, etc. But what we don't know, the key unknown is what will be the extent of the population when we discover it. And if we think about it, if we take a step back, this single unpredictable thing is really the most important thing in terms of the cost of the impact and the cost of eradication. In fact, if the population is large enough at the point of detection, meaning that if the area occupied by the population is large enough at the point of detection, then indeed eradication may be impossible. So we know that there's some kind of relationship going on between how big the population is and how much it costs to eradicate. but we don't know how much it will be when it's detected, because that's random. That's an outcome of unknowns. So we need a way of baking that into the model. But once we have a way of representing the size of the distribution at the point of detection, then we can talk about, well, how much will eradication likely cost? We can talk about what's the probability that eradication will succeed. And those factors can then be brought into the post-mortem model. So the post-mortem model is all about the uncertainty around how large the population will be when it's detected, and how that translates into uncertainty around the cost of establishment. So these are two very simple models that lean heavily into utility and away from biology, but not all the way, I want to argue. All of the components of these models have real life equivalents that we could, in theory, measure, and that makes them easy to imagine. And it turns out that imagination is extremely useful in this exercise. I'll talk more about that later. So the keeping it simple, please, part of the exercise was to keep the number of unknown things to a minimum. And this is where we have to make this really careful trade-off between biological realism and the number of questions we're willing to expose our experts to. Think about it this way. It's easier for experts to think about very fine-grained questions, but if you ask very fine-grained questions, you've got to ask a lot of them. Whereas if you ask broad, general questions, hand-wavy questions, they're more effortful, because the experts are integrating over more things in their heads, and they're very good at that, bless their hearts, but it's tiresome, it's fatiguing, have to give them lots of cookies. But the advantage of the general questions is that you need fewer of them to get a model that behaves reasonably. So there's this wonderful tension in building a model like this one between the detail of the questions and the number of questions you ask. And these things cohere beautifully with the use case to which the model needs to be put. These things speak directly to, I need to make a decision, and so the model needs to represent the outcomes of making that decision as faithfully as possible, perhaps as faithfully as reasonable, without putting too much strain on my experts. So how do we do that? Well, in the case of the gypsy moth, and I'm going to add a quick footnote that wherever I say gypsy moth, I mean Asian gypsy moth and European gypsy moth. And yes, I know they're not the same, but they're going to be for our purposes. Sorry. For the pre-border and border model, there were 12 questions. They were, what are the approach rates of minimal, viable, propagable units on each of 6 pathways, meaning a high, low risk stratification on 3 pathways. I'll tell you what those are in a moment. What are the intervention impacts of 3 different exercises that the ministry undertakes at and before the border? And what are the attenuation rates from the arrival of the probable unit to establishment? Meaning that a probable unit may arrive at a port at a certain rate, but it's still got to find the host material. It's still got to reach somewhere where it can actually infest. So it's not guaranteed that an arriving probable unit will actually, or sort of minimum viable population will actually establish. And in fact, that rate is a really important consideration. So the pre-border border model is simply 12 questions. The post-border model was 6 questions. And those were, what is the expected incursion size at the time of detection under 2 scenarios with the current surveillance regime and no surveillance? What is the cost of eradication at a given size? I think it was 500 hectares, given readiness and also in the counterfactual of not being ready. And what is the success probability of eradication at those given size, at 500 hectares? Again, given readiness, the current state, you know what the traps are you're going to deploy, you know who the experts are, you've got them on speed dial, and not being ready at all. The counterfactual of we don't know what's going to happen. So 18 questions was about as narrowly as we could pare this down. How do we answer those questions? Well, we used structured expert judgment, a well-worn, well-honed foil in the CEBRA toolbox. It's a controversial approach, and I will confess to my colleagues' delight that many years ago I was a great skeptic of structured expert judgment, and I've allowed myself to become seduced by the power that it provides us in answering really important questions in transparent and repeatable ways, and giving us access to a way of thinking that would otherwise be impossible, and giving us a way of thinking about problems like this one that would otherwise be completely out of reach. So we used structured expert judgment, and I'm going to say a few brief words about that. Firstly, structured expert judgment is designed to get information from, I've been a little bit loose here, I'm calling them smart folks, but actually these are experts, but expert is a kind of a loose label. There's argument about who deserves or not deserves, perhaps who would qualify as an expert, and there's a rich discussion about that in the literature. But we chose anyone available in MPI and in New Zealand who we felt confident would understand the principal terms in the questions and be able to provide the information with a degree of confidence. The approach we take is designed to avoid personal cognitive frailties such as anchoring and framing and overconfidence and so on, and also to avoid group cognitive frailties such as groupthink and dominance and the halo effect. I won't say any more about those because we've written about them a lot, but I'd be happy to share a brief report with anybody who's interested. Don't hesitate to reach out. So we use structured expert judgment, and we use the IDEA protocol. The IDEA protocol is a protocol that was invented by CEBRA and its predecessor, and it stands for investigate, discuss, estimate, and aggregate. These 4 key steps. So investigate means that the experts are presented with questions and they use all the resources available to them except not one another. So this is an independent investigation to try to answer those questions. And then the experts are brought together in a comfortable, welcoming environment with many cookies and possibly even coffee to discuss these questions. And in so doing, they surface assumptions that they have made. Ideally, they may have already done this, and they identify the points of difference they have. And they talk about the issues that occur to them in the context of the questions. And often it's the discussion of the issues that's really valuable. They then make a private estimate of the answer to the question, and they don't have to tell anybody what it is. And then these estimates are aggregated with fancy computers and code by statisticians. So that's the IDEA protocol that we use to get answers to the questions. I'm going to give you an example just for context. An example of the structured expert judgment question is: imagine 1,000 random high-risk ships from all countries. How many of those 1,000 random high-risk ships will carry a minimum viable unit of gypsy moth? We have to define a minimum viable unit as being a certain number of eggs or a gravid females or something. We have to define what high-risk ships are, and we also have to talk about the relative distribution of ships from countries. All these factors create uncertainty in the question. So we then encourage the experts to be pessimistic and think of all the reasons this number might be high. It might be gypsy moth season. There might be lots of lights around the ports. The vessels might be poorly managed and poorly curated. It could be crazy. And then we ask them to estimate that upper limit. And then, and I've got a typo here, apologies, we asked them to be optimistic and think of all the reasons that the number might be low. The vessels are coming from low, not high. The vessels might be coming from a long way away. The vessels might be carefully inspected at the point of origin. It might not be in season, etc. And then they take a guess at their lower limit. And then we ask them to take the best guess, somewhere between the upper and the lower limit. And these estimates then inform the study that we undertake. So that's an example of how we carried this thing out. Now, I mentioned the pre-border and border model, and the things that we asked for were the raw exposure on 6 pathways. That's the rate per 1,000 at which these units are arriving that are contaminated with gypsy moth. And the 6 pathways were the high and low risk crossing of shipping containers, ships, and vehicles and machinery. And the risk factor all depended on where they were coming from. There are also 3 interventions. There's border, there's inspection, there's offshore certification and inspection, and there's heat treatment on different pathways. And then there was also the possibility of attenuation, meaning that these minimum viable units arrive at the port, but they still may fail to get to the host material, and that may differ depending on where they arrive. And so we allowed for those to be different. So that's that attenuation factor. Okay, and here's a quick schema of how this model, this pre-border model works. It's just pipes and filters and flows. It's a very simple, essentially linear model of the flow of activity from one pipe to another pipe. It's almost, I guess you could call it a generalized generalized acyclic graph. Okay, so here's an example taken directly from the report, which gives an idea of the kind of information that comes out of this exercise. We have these pathways, I mentioned, these 6 pathways, and the volume is the number of units that travel on the pathways. And we don't know the approach rate. We don't know the rates at which those items carry the units of units of risk. And some of the pathways experience some intervention, and that intervention itself has an impact, but we don't know what it is. So we exposed the experts to these questions, and bless their hearts, they came up with some numbers. So the approach rate, for example, of probable units on the high-risk containers was estimated at 31% by the experts, and on high-risk ships was estimated at about 19%, and on high-risk vehicles and machinery, 24%. And the impact of inspection was estimated at, this is averaged across the experts, I should add, was estimated at about 3/4. The impact of offshore certification and inspection was estimated at 35%, and the impact of heat treatment on high-risk vehicles and machinery carrying probable units was estimated at 94%. When I say the impact, I mean this is the reduction in the flow of viable populations through the intervention. So 1 in 5, let's say 1 in 20 was assumed to be able to survive heat treatment. So heat treatment was considered to be an extremely powerful intervention, according to the experts. Now this all translates to an outcome, a sort of a residual threat, and we've got our residual threat here. There's a residual sort of number of pests, and there's an establishment probability. The residual is per 1,000, if I remember correctly, and there's an establishment rate on the right-hand side, and you can see that the establishment rates, these are per pathways estimated establishment rates, sum to about let's say a 0.0165, so about 1.6 incursions per 100 years. So the overarching picture was very low risk. Now, I have to say there was an unsatisfactory, I'm going to put my hand up and confess to an unsatisfactory element to this, and that is that we did have to massage with the experts' input. We had to massage the outputs a little bit because it turned out that the expected number of establishment rates with the raw elicited data was too high and unrealistically high, which would have implied that the biosecurity system was unreasonably highly valued. So we wanted to be really conservative about this. So we had to adjust the figures down. And that's what I'm referring to as shenanigans, which is possibly a little dismissive of me. But there we go. I'm drinking a nice strong cup of tea and I feel better already. So what about the incursion impacts? We're going now to the post-border part of the model. And remember that I mentioned before, the impact of an invasion is affected by a range of factors, host material and climate and pathways and the value of the resources and so on. But the population extent at the point of detection is really critical. And you can't anticipate that. You can say what you think affects it. You can say, well, I think if I spend more money on surveillance, then the population extent when I detect it will be smaller, and you'll probably be right on average, but you don't know what it'll be. And it turns out you really need to know what it'll be in order to know what's going to happen. So how do we solve that problem? Well, we use statistics. So what we did was we broke the post-border part of the model into two key components. Firstly, when is the established pest detected? Meaning, what is the area occupied by the population at the time of detection? And we use the Weibull distribution to help us with this. And we also then, given that we pretend we know the area occupied, although we represent it by a probability distribution, promise no equations, then the cost and the success probability of eradication as a function of that random variable will tell us what the outcome will be conditional on that establishment. So we essentially, it's like we average across the unknown thing, although we actually, to be more specific, we integrate it across it, which is much better. Okay, so here is a graph that shows us what the experts thought the area infested would be at the time of population detection. We've got three densities here, and I'm going to tell you what they are one by one. The attractive bluey mauvey distribution is the expert opinion of the area with the current system. So you'll see that it ranges from about 10 to about, let's say, 10,000 hectares. There's 3 bumps because the experts didn't all agree. The highest value was just north, so to speak, of 100 hectares. So the mode was just larger than 100 hectares. So that was the most popular value, although as I observed, it's actually got more than one mode, which is honestly a bit distressing. Okay, the green plot gives us the same outcome, but with under the counterfactual that had there been no surveillance. And what that shows us is if there's no surveillance, then the expected area occupied shifts to the right. It gets much bigger, and it really seems to range from about, let's say, 100 to, let's say, 100,000 hectares, which is much bigger, and consequently much more expensive. Although how much more expensive, we are yet to determine. And the last of these densities is the orangey sort of density, the burnt orange density, and that's taken from the GERDA database. And honestly, I don't remember what GERDA stands for because every time I say it, it just reminds me of the things we build bridges from. But it's online, and if you search for GERDA, you'll find it, and it's a wonderful database of eradication attempts and the cost of eradication. And this is about 30 to 40 instances of eradication of fruit fly that we've got the area infested at the time of detection for. And you can see that it pretty much covers the experts' estimates, although there is a greater leaning towards early detection in GERDA. So GERDA is, so our experts perhaps are a little bit pessimistic with regards to how quickly it might be detected. But it should also be noted that the GERDA database mostly is populated by eradication attempts from the United States. And the system is quite different there. For a start, they're looking for it very, very actively. Okay, so that's how we handled this. We can imagine now that for any given area infested, I could just take a random number from that distribution and I could push it through the equations that are to come. And then if I do that with all of them, with enough of these values, then we'll get an idea about what the spread of the cost is and what the impacts of our measures are. And that's what we're going to do. So here's a graph now of the cost of eradication. This is data taken from GERDA, but model fitted by CEBRA. And what we see is that the cost increases pretty much linearly in this log, in these log axes. And what we have here are the red and the green symbols. The red and the green crosses are the estimates at 500 hectares of the cost of eradication. The green is with the current system, and the red is with the counterfactual system of no readiness. And the dots are the averages, and we can see that the average is just about tenfold. So the experts estimated that the cost of not being ready the cost of responding, the cost of eradicating a pest that was in all ways like gypsy moth, but not quite like gypsy moth, would be about 10 times larger, based on the fact that we really think we know what we're doing when it comes to gypsy moth, because of our extensive experience with eradicating gypsy moth in other settings. So that's a really interesting and indicative outcome about the value of research leading up to an eradication, that the cost was estimated being about 10 times higher if you weren't ready. Now, we also have from GERDA the probability of eradication success, the eradication probability as a function of the size of the infested area at detection. Again, we've got this log 10 graph going on for the x-axis, and we have the model again. The data comes from GERDA, and the model is fit by CEBRA. And the red and the green crosses have the same interpretation. Now they are the probabilities of success, and the green and the red dots are the averages. And I say that this was overruled because we fitted the model and we presented it to the experts, and the experts said, well, actually, this is way too conservative. It is very, very unlikely that, given all that we know, that we would fail to eradicate. I mean, it's honestly, it's not impossible. So this was a judgment call. It's easy to imagine scenarios under which eradication might not be attempted. But regardless, we followed the experts and said, okay, well, we'll boost up the probability, the probability of eradication success. But this was an area of considerable discussion, heated. What about what about the cost of management if the establishment succeeds, if eradication fails? Another typo, my apologies. So we assume an annual cost of $50 million based on some research that we found, and I'm happy to share that with people. And we assumed a 5% discount rate. So the overall impact, the net present impact of an uneradicated incursion was assumed to be $1 billion New Zealand in 2020 dollars. And here's the fact of the matter is that that's probably not right, but it doesn't really matter. It's huge. It's very big, but it's within the order of magnitude of what it would cost to eradicate a really, really big incursion. So there was work done on this, and we decided to run with $1 billion as the net present value of an incursion. And happy to discuss that, but it's a valuable thing to contemplate. Okay. So what are our sources of uncertainty in this grand challenge that we've set ourselves? Well, we elicited these values in the pipeline and the outcomes for the experts. Those are all uncertain. We modeled eradication costs, and we modeled eradication success probability. The discount rate was uncertain, and the size of the incursion at the time of detection was uncertain. And the economic impacts of the failure to eradicate was uncertain, and the shenanigans were also uncertain. So we represented all of these uncertainties using scaled triangular distributions, and the details aren't important right now. Happy to discuss those over a hard cup of tea at some other time. What are the results then? What are we talking about? Okay, so this is the cost of an incursion, a single incursion, estimated cost in the current scenario, $40 million. In the scenario where it's gypsy moth, but there's no surveillance, let's call it $60 million. In the scenario where there was no readiness, but there was surveillance, which is actually kind of impossible because you wouldn't do surveillance for a pest that you aren't ready for, or that would seem absurd. Also $60 million, totally coincidentally close to the other one. And finally, the real counterfactual, I would argue, which is there's no surveillance and no readiness, that's about $70 million. So the average cost is about twice as much, give or take, without readiness or surveillance for that overall, for that outcome. Okay. So now let's talk about the counterfactual scenarios that we were looking at. This is now capturing the uncertainty that I was referring to earlier. The uncertainty The expected cost of incursion is in the attractive orange on the left-hand side, and the mode is, let's say it's somewhere about $20 million, but the average is 40, as I alluded to earlier, but it could get up to $100 million. Certainly $75 million is not out of the question. There's a very long right tail because of all the uncertainty that we were talking about earlier. Now, what about the additions to this status quo? So the scenarios on the right-hand side should be considered in addition to those scenarios. Remember, the increase was about $20 to $30 million, but it could be as high as another $75 million or even $100 million. So the idea that it pretty much doubles the expected cost of incursion is about right. Okay, so these are the counterfactuals, and this is telling us what happens if you have no surveillance. Then an incursion will cost you a lot more. And if you have no readiness, an incursion will cost you a lot more. Basically, half as much again. And how does this translate in the context of the pathways? And this is where the rubber really hits the road. What about these measures? The measures, remember, that we were undertaking we were doing inspection of high-risk ships. We were doing, high-risk containers. We were doing certification and inspection of high-risk ships and heat treatment of high-risk vehicles and machinery. And the expected saving in terms of the number of incursions per year is in the saved column there. And the heat treatment of the high-risk vehicles and machinery is saving us about a quarter of an incursion per year, which translates to about $8.1 million New Zealand per year. Now, straight away, the arithmetically inclined amongst you will have said, but hang on a moment, 8.12 divided by 0.26 does not equal 40. And that is absolutely true. And all I'm going to say about that is no equations. And also I'm going to say Jensen's inequality, and we can talk about that more over 2 cups of hard tea in the future. Now, remember I said this was uncertain? Well, the standard deviation is actually a similar order of magnitude to the estimate we've got here. So it's really uncertain. Let me say more about that here. These are the distributions of the expected savings, annual savings of these investments of these measures against the arrival of gypsy moth. So high-risk containers and high-risk ships, those treatments are not expected to save very much. And the reason is that there's a low expected arrival rate. On the other hand, the heat treatments, which save, as I mentioned earlier, an average of 8 million, could be saving anywhere up to $10 or more million per year. But there's a lot of uncertainty about that. And some of this uncertainty is irreducible, and some of it can be reduced. So a useful exercise going forward might be to undertake an error budget and see where the uncertainty is the highest. Okay, so that's the estimated impact of these interventions, these layers of the biosecurity system against gypsy moth. But before you ask yourself, well, is $8 million a year worth a quarter of a gypsy moth incursion? I want to say that the heat treatment also has impacts against other pests that really need to be factored in. If you're thinking about this in a holistic way, then we need to not ignore the possibility that these factors have these measures have a multifactorial impact against biosecurity threats. And our friend BMSB is always ready to arrive given a chance. Okay, so where do we end up then? So in terms of lessons learned, as I mentioned earlier, we've got to make this trade-off between general questions, of which there need to be only a few, and fine-grained questions, of which you have to have many, but they're less taxing. And what I mean by less taxing, for example, is you might say, just to pick on BMSB, what's the average arrival rate of BMSB per year? But then you might acknowledge, well, hang on a moment, and that's one question, but then you might acknowledge, well, hang on a moment, there's an off-season and an on-season. What's the average arrival rate during the off-season, and how long, the on-season, how long is the on-season? When does it start and when does it end? So that's 3 questions. And 3 questions takes longer to answer for experts. It's harder to think about than 1 question, but these 3 questions are more fine-grained and will provide greater biological realism and possibly more utility. So there's always going to be this tension between how many questions you can ask your experts. And indeed, there's an optimal number, I would contend, for any given situation. There's an optimization challenge behind specifying which questions to ask and using those questions to come up with a model that represents the key processes so that meaningful questions can be asked and answered with meaningful measures of uncertainty. And there's this beautiful balance, this very delicate balance that has to be struck. That's the first thing. The second thing is we do have border data and establishment data often, but we need a proactive way to use them. And how to do that best is an open question. In this project, what we did was we did all the analyses, and then we came back to the experts and said, actually, look at this number and that number, and it's quite different. What can we do to sort of ease in a kind of correction? And we came up with honestly, a not very satisfactory shenanigan. Much better if we could do it and we could tie these in to simple questions in such a way that the answers are guaranteed to cohere with the things that we think we observe. Not fully match, but at least be close to. And finally, well, not finally. Next, if the quantities do have a natural rank, for example, how much would this cost in the counterfactual? How much does this cost with the current surveillance, and how much would it cost in the counterfactual of no surveillance? It should cost more if there's no surveillance, but based on the way questions were asked, it was possible that it could randomly just cost less. And that meant that there was some uncertainty around these distributions that there didn't need to be. There was some unnecessary uncertainty around the outcome. So I think we think it's important to cook these questions in such a way that natural rank gets preserved. And there are a couple of ways to do that, but they make the questions seem more difficult. So we need to work on that. Because we don't want to fatigue the experts. They're already incredibly expensive in terms of cookies. And finally, I gave a presentation that was less detailed and less sparkly than this one, but it was still beautiful, about the brown muscle version of this project to New Zealand MPI. And I obviously haven't presented any of the results here, but unlike that version, the reviewers who reviewed this version of our model really quite liked it. Which just goes to show how important it is to choose the right reviewers. And the final point I do want to make before I open us up to questions is that, again, I just want to touch back on this issue of structured expert judgment. Increasingly, we've been using this to solve what seem to be otherwise irredeemable problems. And so I just want to say that the new motto for CEBRA is going to be, it's better to light a candle than curse the darkness. And I'm going to outsource translating that to Latin, and we'll put it on our coat of arms. Thanks so much for your attention today. And I look forward to the question period.
Well done, Professor Robertson. I didn't even have to turn the camera on early, so thank you for that. I think we've also got a couple of other people just joining us at the moment. Just give me 1 second. We've got a few questions that are coming through. Can I just check, is Michael Ormsby online as well? I can't see you yet, Michael.
I'm there.
Very good, thank you. An excellent presentation. Now, we're going to throw it open. I'll go to the hands up first, and apologies because I'm trying to operate off my laptop here, but I can see Mark Wattam has his hand up, so we'll go to you first, Mark, and then I'll read out a couple of the questions that are in the channel there. So fire away, mate.
Thanks, Andrew. Entertaining as always. It's really interesting work, and I think it is something we should, as a department, apply more often. And I think the reason I say that is based on what you guys have done collectively. Really good stuff. Russian wheat aphid comes to mind. And I know Russian wheat aphid was one of our top 10. We don't want it. It's going to destroy our wheat industry. And it arrived, and I'm not an entomologist, but doesn't seem to have done much out there. And one of the reasons, I think, is because a lot of the existing crop management processes can manage these things. So Just a comment. So thank you very much, Andrew, for a really interesting concept.
Thanks, Mark. Let me engage with that if I could. You're absolutely putting your finger right on the key button, and that is the goal here was to say, even in a very first order approximation way, what are the important things to do against pests? If we're handling the risk pre-border, or if natural forces are handling risk pre-border, then there's an open question about the importance of other measures and layering of measures. And it may well be that Russian wheat aphid being a great example, it may well be that the ultimate impact is its own risk mitigation measure. Thank you.
Very good. We've got a couple of questions coming through there, Andrew and Michael. So this is from Karen Wilson. With the area occupied at time of invasion, was there any pattern to the modes? For example, did readiness/surveillance experts differ from risk analysts, or entomologists differ from others?
That is a wonderful question. And the answer is my sample size is quite small. So on the one hand, that makes me wary of drawing general conclusions. And on the other hand, it makes me wary of providing insights that might lead back to the identification of individuals. So I'm afraid I cannot answer that, both because of ignorance and delicacy.
Well played. And this one's perhaps for both of you, noting we've got obviously issues on the doorstep there with foot and mouth and others in the region. This is from Terry Sim. What lessons from this research are applicable to the biosecurity investments Australia and New Zealand make to mitigate the impact of a foot and mouth outbreak? I'll go to you, Andrew, first, if you.
So we haven't applied this formal model to foot and mouth disease for either Australia or New Zealand. It's a very interesting challenge. Michael, as I recall, I'm gonna demonstrate quick hands at the breakdown, but I'll give you a feed. As I recall, there's a B3 project that is about to look at modeling the arrival and behavior of pathogens in the IBRAM modeling framework, which is like this one but on steroids. And we may be able to pick up some of that and deploy it in this framework. But there you go, Michael. To you.
Yeah. Thanks for that. Quick hands. So one of the lessons would be that we measured the economic impacts of potential economic impacts of spongy moth, as it's now called, not gypsy moth anymore. It's culturally unacceptable. Spongy moth, but of course we didn't look at social, cultural, health. There is some health stuff, or environmental. So if you look at the numbers, you could see that the investment cost was probably at most twice the value, with normally investment criteria would be something like 5 times the value. So you've got to measure all your values to make sure you're measuring the true investment cost, if you like, or the relative benefit of that investment. But as a way of it's always been a big struggle for us to measure what the value is of readiness and surveillance, and compared to the costs. And this is a step to do that. This is a way that we tried to do this. It looks like it turned out pretty well. Recognizing the fact that we didn't measure really all the benefits, because we couldn't look at those other costs that are harder to measure. But a piece of work we're kicking off at the moment with CEBRA is going to have a good go at trying to measure all those other costs as well. So we could expand it with those extra values to make it a bit more of a true representation. But foot and mouth is itself probably a bit there's also the same challenge of measuring all those different impacts it will have if it does get into a country.
Thank you for that. And yes, that was a bit of a curly one, but appreciate. We've just got another question coming in here from Stu Hutchings. Thank you, Stu. Great presentation, Andrew. Interested to know what the reviewers did not like about the brown mussel version of this model application. You're on mute, Andrew. On mute.
Thank you, Stu. That's the one I didn't present today. No, what the reviewers didn't like its biology. It was too high level for the reviewers. It was they wanted more parameters and more fine distinctions that the remit of the project could support. The goal of the project was to produce something that could be rolled out relatively cheaply across a wider range of pests. And I think the review comments from the marine biologists were probably almost as long as the report itself. That being a little facetious there, but certainly would not occasion a model that was easily extendable to a range of other pests.
Just had one more come in, Andrew, from Ursula Torres. Thanks, Ursula. How can we estimate the benefits of interventions for one like the species of the, what are we calling it, the spongy moth, Michael? Thank you for that, that are translated to manage other species?
That's a great question, Ursula. And the answer is we would need to build a similar model for the same species, for that other species, for example, BMSB, and then the benefits. We need to be sure that we don't double count the benefits. That is that they wouldn't be attacking the same values. But there are ways of resolving that tension. But then essentially with that caveat, they could be added. So I'm going to say added with a lowercase a rather than a capital A. We are added with qualifier.
Thanks, Andrew. I don't know if we've got any other questions coming through, but I'm just going to throw it open to everyone in case there's anything that you want to add. Feel free. Give you a couple of seconds. All right, Karen, that's a long one. Just thinking that if you do get similar weird modes in the data, Andrew, over time, more models, bigger number of experts, then a pattern of discipline may emerge that maybe wouldn't expose individuals to the same extent, acknowledging that several of your experts will be used repeatedly. So any analysis would need to factor that in.
Agreed. Yes, agreed. Absolutely.
Perfect. Thank you, Stu. It said the driver for his question was the applicability of the model to the marine environment, Andrew.
Yes, so Stu, very good point. And in fact, that's why at the beginning of the presentation, I was very fastidious about saying that the utility needs to trump biology. In a regulatory environment, as you would appreciate better than anyone, I expect, the impetus to make a decision needs to trump, let's say, biological niceties, if I could put it that way. I don't mean to sound dismissive of biology, not for a second. Biology should inform what we do, but if a model takes 10 times as long to build because it's biologically more rigorous, but then that the decision space is closed in that time, or even in extremis doesn't address the decision space, then it's of limited utility.
Yeah, and I'd add to that. In the spongy moth space, we had data. We had some data that we could use to correlate the experts' judgment. So we could say, okay, you've overestimated here because we've got some data that says that looks like an overestimation. In the marine space, it was much less data, much less evidence we could use to to correlate, to confirm, if you like, the expert judgment. So you asked experts to review it, and they said, oh, you need to use all this data because that's the data we produce and it justifies our existence, perhaps. And that's fine, but we couldn't dismiss that by saying, yes, but we've correlated it, because we couldn't do that. So it just sort of left it hanging in a sense. It doesn't mean that what we did was wrong necessarily, but we couldn't confirm it against that review like we could with the spongy moth, I guess.
Yeah, I've doubled down on what Mike said. This exercise isn't about what is true, it's about what is useful.
Couldn't agree more. Look, in the interest of time, I think we'll close it there. We will still leave the chat open. If there's anything else, we'll try and get back to you. But I just want to thank Professor Robinson for his time. It was a really interesting presentation, and thank you, Michael, as well, for joining us all the way across there in the ditch, the other side of the ditch. It was a really good conversation and useful information, so I hope everyone got a lot out of it. Just flagging for those of you, as we're now branding it, our CEBRAnars. There's another one flagged for end of next month, 30th of June, and it'll feature an NZ MPI project focused around expediting risk analysis development. So please keep an eye out for that one. That should be a really good CEBRAnar as well. But thank you everyone for joining us today. Really interesting conversation and topic, and I know, Andrew, we could talk about this for a lot longer, but do appreciate you getting through in the time. So thank you all. Enjoy the rest of your week.
Thanks everyone.
To Jason and Chris as well for organising all of this. Well done, gents.
Big thanks to your team and to Lisa. Thank you.